Okay, let us start maybe. Uh, let me remind what was the summary of the previous lecture. That there are several different equations, like probably I can on the right. So there are equations like wave equations. Equals to f or to 0, and good boundary conditions for this equation look like this. We have a u and ut fixed on this boundary, and we have so it is a initial condition, and we have u equals to something or a derivative of u. Ux equals to something. This is called Dirichlet boundary condition. This is called Neumann. And there is the same situation for wave equation and for the heat equation. And in principle, there are also other boundary conditions, like u of 0 equals to u of L. The derivatives are also equal. And there is in principle another option that is called mixed boundary condition. So this works this way for the wave equation, for a heat equation, and if you study, and also this should work for Klein-Gordon modification of the wave equation. So in principle, we can add here plus gamma u, and it will be the same. It will only change dispersion law. Plus, maybe, yeah, like this. And if you work with Laplace equation or Poisson equation, also possibly with this modification. And then we don't have initial value problems. We only have boundary value problems. So this is initial values. So in this case, we have again all this variety of boundary conditions at the boundaries. And all this can be called boundary value problem. So, and now let us first focus on these two equations and look more carefully at possible boundary conditions. Mm. And let us first restrict to a simple case of the interval from 0 to L. So the simplest example, which we already studied, corresponds to periodic boundary conditions. In the sense that u of 0 equals to u of L, and let me put here t, and u of ux of t0 equals to ux of tl. So if you want to solve this problem, we can use the simplest version of the partial Fourier transform. Mm. Now we can say that this u of x and L is sum over integers. Sorry, of t and L, t and x. Sorry, un of t times e to. But what should we put in the exponential? What do you think? If we have x changing from 0 to L. Oh, I would prefer positive exponential here, but yes, 2 pi I x over L. So, and we know that it is, in a sense, we have already proved quite long ago that this transition from coefficients un to the function of t and x is one-to-one correspondence on a good subclass of functions and such sequences. So this function should be continuous, or maybe at least once differentiable for convenience. And this series should be convergent. So the inverse transformation that constructs these coefficients from the function is this integral, that un of t is dx e to the minus 2 pi I. Sorry, I forgot n here. I x n over L u of t and x What do you think? What should be the coefficient in this integral? So that this actually works. Hmm? What? Uh, oh, yes, 1 over L is the correct answer. Because it integrates from 0 to L, so uh, and the only term that survives this integration is the one where we have 1. When this exponential cancels some other exponential, because if this exponential oscillates, then its average is 0. So they are all orthogonal. Yeah, so we are able to reconstruct this function back. And if you rewrite the wave equation for these coefficients, then we see that un of t to primes plus or plus 2 pi n over L squared u n of t equals to 0. So there are two different cases when n is different from 0. So then there are two solutions that n of t is an well, in principle, we can write them as exponentials in time, or we can write sine and cosine functions. It's the same. Maybe let us write sines and cosines. Maybe, or maybe, no, I don't know. Let us write exponentials. Hmm. So, and if we combine this exponentials with this exponentials, we see that all of them are functions of t plus x and the t minus x, as in principle expected. Mm, uh, so it was from the wave equation. Uh, uh, another question: what happens if we turn this equation into Klein-Gordon equation? So in this case, we have another term, in a sense, utt minus Laplacian of u plus gamma u equals to 0. So what will it give for the mode expansion? Yes. Uh, so this equation will look like this. And people also denote this gamma by m squared. Maybe let us use this notation, which has a meaning of plus. So solution of this equation now will contain exponentials with square roots of these expressions. So squared plus m squared plus complex conjugate. And this is called dispersion law, but it's just a name. In a sense, we can solve this equation and see what we get. And also, we notice that this solution is not as simple as for the one-D wave equation, because there is no explicit formula like u of x plus t plus u of x minus t. Yeah. So in this example, when we solve a heat equation, then in terms of modes, it looks like this. And its solution is also obvious. So, but let us try to study different boundary conditions for the same equations. So it was the simplest case. Let us now try to study zero boundary conditions, or which are the same as directly boundary conditions. So I already told this at some point, but let us repeat this construction. So we can start from our problem on a circle, from 0 to L. And maybe let us take it from 0 to 2L. And we notice that there is a symmetry that maps x to minus x, which can be drawn as this mirror symmetry of a circle. In a sense, it can be thought as a reflection along this line. So acting on the space of functions, this maps f of x to f of minus x. So we have a space of functions maybe, or probably it's better not to write there. We have a space of functions on S1. These functions can be differentiable functions or continuous functions, like whatever functions we like. But independently from this, there is this operator acting on the space. And this operator commutes with the Laplacian operator. In the sense that if we take if we first take Laplacian of f and then compute it at minus x, it will be the same as to compute f of minus x and then apply to it Laplacian. Because Laplacian is just a second derivative, and or if we have many components, then only one second derivative will be affected. So it is just a statement that if we compute a second derivative of f of minus x, then it is minus 1 squared times f two primes of computed at minus x in the statement. So since this operator commutes with Laplacian, it makes sense to say that we split the space into two spaces of odd and even functions. Which means that any function can be written as odd and as a sum of even and odd function. And of course, this odd and even part can be written as a symmetrization. In the sense, this formula reads literally like f of x plus f of minus x over 2 plus f of x minus f of minus x over 2. Right. And now the basis in the uh, this space of positive functions is given by cosines. Basis in this space is given by sines. Mm. So mm, we can say that mm, uh, or saying in a little bit different way, that if we apply this Fourier transform for the order function, uh, mm, or maybe first for the even function, if we apply this Fourier transform for the even function, we will have only cosine combinations of coefficients. Sine in this case of pi n over L x and f minus of x will be sum of bn sine of bn over Lx. So in principle, we could use the same sine and cosine Fourier transform from the very beginning to write any function on a circle, but that expansion with exponentials was simply shorter. Although we have complex coefficients if you do in that way. So. So any functions can be written as a combination of odd and even function on a circle. But if we are interested in in different boundary conditions on the interval, we can simply restrict on one half of this circle. So we have, so in principle, we have some function that was defined on the whole circle and was odd or even. But for our purposes, we can say that this function was defined only from 0 to L, because all functions because there are no extra conditions on this function except its boundary conditions. So we can take an arbitrary function and complete it to a function on a circle using one or another prescription. And in this way, we obtain two kinds of Fourier transform for this interval from 0 to L. So how should I call it? It's not a conventional notation. I just invent some name for this Fourier transform. So it is cosine Fourier transform. So for a function that has a vanishing derivative to sides, we can write this formula. Fx equals to an sine of pi n over L x. And well, probably I don't want to compute it on the blackboard. I will maybe do, no, I don't want to do this, but we can do this at home to compute a scalar product of such cosines and find the norms. So here we have sum from n equals to 0 to infinity. And the inverse Fourier transform, therefore, let us put fn's. The inverse Fourier transform will be then some coefficient from 0 to L. Oh, this coefficient is actually 2 over L. So we have this basis functions, and if we draw them, we get pictures like this. This is for n equals to 0, and just constant 0 to L. For n equals to 1, same picture for n equals to 2. And so on. And these functions are called normal modes. Actually, all of them are called in this way. And the idea behind this is that if you take eigenfunctions of Laplace operator and look at their evolution, then this evolution, both with the wave equation, Klein-Gordon equation, heat equation, will look very in a very simple way, and there will be just oscillations with a given frequency. So, and the full solution is a combination of such normal modes with appropriate trigonometric coefficients. Yeah. So it was one Fourier transform that we could see here. And then we can of course take another Fourier transform. So in this case, normal modes look like this: 0 to L n equals 1, n equals 2, and so on. We expand any function on the interval from 0 to L or over such functions. And we can reconstruct coefficients by the same formula. Simply multiply and integrate. But so far we see that using this naive idea that we can extend a function to a function on the circle from 0 to L. So using this idea we can get this Fourier transforms convenient for both Neumann's boundary conditions and Dirichlet boundary conditions. Like here and here. But what can we do with other two combinations of boundary conditions? So what? So the idea is also simple because even when we switch to this interval, we still have another symmetry. Namely, there is an option to take mirror symmetry of this interval itself. So we can take E2 that maps x to L minus x. And we act with this E2 on this space of functions that vanish on two boundaries. So what can we say about these three functions? How does E2 act on them? So let us call this f phi1 of phi1 of x, phi2 of x, phi3 of x, and so on. Yes, of course, because yes, L over 2 is a fixed point, and all other points are permuted. So yes, thanks. So, well, it's not a surprise that this operator acting on the eigenfunctions of Lavoisier operator acts by numbers, because these two operators also commute. Because well, it's the same argument. If you compute second derivative of function of L minus x, then overall minus sign appear twice because derivative is second, and it's the same as to first take second derivative and then substitute minus x. So it's not surprising, but it is very convenient now, because if restrict to interval from 0 to L over 2, uh, mm, uh, we can restrict to even functions. So if we restrict to uh, even functions which correspond to odd numbers, like 1, 3, and so on. In principle, we could restrict to this subset of functions which are odd with respect to this reflection, but it would give us the same basis as we already have. We will simply take half of signs on twice smaller interval. So it's not interesting. So this set of functions is interesting. So using this symmetry, we can introduce another Fourier transform for the interval uh, 0 to L over 2. So now the sum goes over oh, from n equals to 0 to infinity, but uh, functions themselves will be sine of 2 pi 2n plus 1. Sorry, it was pi originally. Yeah, sine of pi 2n plus 1 x x over L. Or if we want to write everything with manifest L over 2 notation, we can do like this: divide by 2, and then this number becomes n plus 1 half. So in this case, this normal modes look in obvious way, like this. Mm, this, and so on. So the moral is that if you work with functions on the interval, we can choose whatever transform we like. The only problem is that there is this last case of mixed boundary conditions, and it is more complicated because if you look for the space of functions that satisfy such boundary conditions, we need to solve some transcendental equations, and we cannot describe them in such a simple way. So, do you have any questions on this? So, in this way, we managed to construct solutions of these equations explicitly on rectangular domains, because we could simply perform this Fourier transform with the initial conditions and then run the evolution that acts in a pretty simple way on each of these functions. So what can I say more? And let us also notice one thing about the answer to this problem. Maybe here is this. So it is a linear combination. So this is a solution for the Klein-Gordon equation. We could take any other equation, but sorry, sine of 2 pi n x over L. Actually, so the solution is a combination of expressions when we multiply functions of t and of x only. So we can write it as a combination of some an's phi 1 n of t, phi 2 n of x plus bn. So this result is a combination of such a function that depend only on the products of different functions of t and x. And this is called the separation of variables. So in our case, it appeared explicitly from some natural assumptions, like we wanted to diagonalize different parts of this equation because we could diagonalize translation operators, but if we know nothing about this, we could simply ask a question. And can we solve this Klein-Gordon or wave or whatever equation using such an ansatz? So we could just substitute this expression uh, into our equation. So what happens if we do this? So this is 0, and if you take this equation and divide by phi1, phi2, what will we get? So who can tell what appears in the answer? Hmm? Oh, the question is what do we get on the right hand side? What expression? Yeah, so there will be terms. So of x plus m squared. So we get this expression, and since our ansatz require this to be equal to 0, and each of them depends on its own variable, the only option is that these two are constants. So this one should equal to some lambda t, lambda t, this one should equal to some lambda x, and this one is constant. So we'll need to solve equations like phi1 to primes of t equals to lambda t, phi1 of t and then that lambda t minus lambda x plus m squared equals to 0. In principle, we could get this solutions by simply solving this equation on the ansatz and then take arbitrary linear combination. But this knowledge about the Fourier transform tells us that this solution is actually a general solution of this equation. And this approach has further generalizations. So far we applied the separation of variables to rectangular regions. But of course, there are other symmetric regions. For example, there are circular regions, and there are spheres, and actually there are other coordinate systems where we can also perform this separation of variables. So something like this can be done also in other situations. And in that cases, these equations will not be as simple as these ones, but there is still a general theory that describes those cases, and we will study it a bit later. Yeah. So. It was all this was more or less about existence of solutions, but actually in this particular case it was also about uniqueness, because we know that there is one-to-one correspondence between functions and their Fourier transforms, and we were able to solve these equations for images. But for example, if you are in the situation when we don't have this constructive way to solve this equation, can we prove at least uniqueness of solution in some universal way? And the answer is yes. And I'm going to tell about this now. Do you have any questions about this part? Okay. So let us first study the wave equation. So let's consider on this simple case with 0 on the right hand side. We have u of t and x. We have some boundary conditions, which can be either Dirichlet or Neumann. For example, let us consider Dirichlet boundary conditions on some boundary in the X space. So there is some domain D, and we say that u of t and x restricted on D, on boundary of D, equals to u boundary of x. And there are two initial conditions. U of 0 and x equals to u0 of x. Ut of 0 and x equals to u1 of x. So suppose that we have two solutions of this equation. But wait, actually, yeah, when I put here 0, we could put here arbitrary right hand side. So suppose that there are two different solutions. If you take the difference, so what equation will they satisfy? So equation is linear. So what are the equation satisfied by this? Mm-hmm. Yes, thanks. And also initial conditions are 0 as well. So u t minus Laplacian of u equals to 0 with u 0 equal to u1 equal to 0 and u boundary 0 as well. So we need to show that there are no solutions to this equation different from 0. So we need to prove that and to do this we need one tool. This tool is called energy functional. Which is defined in the following way. So it is a functional in the sense it is a map from the space of functions on this domain, which maybe we can call we can take C1, but it's for example. But this condition should not be that strict, of course. The the only thing we need is that this functional is well defined on the functions we are going to substitute. Yeah, so this functional maps from the space of functions to real numbers. And in this case, there are even positive numbers. So it is defined by the following formula. Let me, how should I write this? E of v of x. No, I write it like this. E of v of a character that describes this as it denotes this function is the integral over this domain. Maybe no. When I introduce a new variable u, which depends also on time t, maybe yeah, I should have written here find the functions of d times r times r. This. Maybe it's better to write what it equals to. So it equals to an integral over this domain of dnx 1/2 of ut of dnx squared plus a gradient of u squared. Right, so we are taking an equal time slice. Have time. We have domain D. And we are integrating over one time slice. So this energy in principle depends on time, and is given by this integral. So is the definition clear? So we can take an arbitrary function that depends on t and x, take this expression and integrate over some equal times slice. There is no integral in t in this formula. So why am I introducing this object? Because although it depends on time, explicitly there is a statement that if we take a solution of our homogeneous wave equation, then this energy is actually constant. And this should be checked by explicit computation. So let us do this. Here you have ut times u second time derivative. Here we have gradient u times gradient of ut. So we see that in this term we could replace tt with a Laplacian of u because it satisfies the equation. But we need then to cancel this Laplacian with something. And this can come only from this term. So to obtain this, we subtract total derivative from this term and rewrite everything like this. Oh, wait, why did I put minus here? Sorry. Minus plus on u times ut plus gradient of ut times gradient of u. Do you agree with this expression? So, no, because gradient of so are you familiar with such kind of computations or not?
Using vector calculus theorem?
Yes, of course.
It's been a while. Stokes theorem.
Mm.
You want to relate the readings of the ball from the surface to the volume.
Mhm. But here you can actually, so let me maybe use another blackboard and write the same computation without vector calculus, just for one dimension, and then we can write this component wise. So it will be the same. So we just integral in dx, 1/2 of ut squared plus ux squared. So does this become does this look fine? So when we differentiate this product, we get uh, wait, no, there should be ux, yes. dx. So when we differentiate this second u, we get this term that cancels. When we differentiate first u, we get this term as it should be. So it's kind of integration by parts written without mentioning explicitly. So now we can say that these two terms cancel because of the wave equation. And this integral, for example, from 0 to L, this integral can be computed. It is ut ux from 0 to L, but it equals to 0 on both sides, because if we have a Neumann boundary condition, then the time derivative is 0. If we have Dirichlet boundary condition, then the time derivative is 0. If we have no Neumann boundary condition, then ux is 0 explicitly. So in either case, it is 0. And here you can think that there are simply more ux, uy, and so on, and all this computation, all this vector calculus simply takes care of this fact. So in this case, this elementary computation will be called Stokes theorem. So again, these terms cancel, and we get the integral over the boundary. N times ut gradient of u. So it is again 0 for the same reason, because for Neumann boundary conditions this term vanishes. For Dirichlet boundary conditions this term vanishes. And you might ask what happens if we try to do the same for mixed boundary conditions. And the answer is that we would need to add some boundary terms, because these mixed boundary conditions are physically described by additional springs that are connected to the ends of this string. So there is some spring connected here, and we should include the energy of this spring into the formula for the total energy. For Dirichlet Neumann boundary condition, we have nothing like this. Okay, so we see that energy is 0. So first know that E of t is constant. Then we can compute that E of 0 is 0 because initial conditions are 0. And so this energy is constant for all possible times. So we know that the integral of 1/2 ut squared plus gradient of u squared equals to 0, and therefore both ut equals to 0 and gradient of u equals to 0. So u is constant. And since we have initial conditions that equal to 0, this constant is 0. So that's all. End of proof. And by the way, if try to formulate boundary values for the wave equation, then we can write very simple counterexample for uniqueness. Uh, So this is what I wrote last time, but in more general case. So you can consider a wave equation on a square from 0 to pi t and x, and uh, you can take u of t and x equal to sine of x times sine of t. This kind of function. Well, I can't draw it properly, but there is something that vanishes at all these four boundaries, but is non-zero. So that's another illustration why this problem is bad. So it has problems with uniqueness, and it also has problems with existence. If you try to impose some different boundary conditions on different boundaries. But if it is a proper wave equation with initial conditions, then there are no such problems. Do you have any questions on this? Okay, let us now try to study this for the Laplace equation. So in that case, everything is time independent. So we can simply consider e of u defined as integral of 1/2 gradient of u squared dnx over this domain. And what we can do here is again integration by parts. So we can write that this integral equals to 1/2 times divergence of u times gradient of u. So when we act with gradient, we get gradient squared when it acts on the first term. when it acts on the second term, we get Laplacian. So that second term should be cancelled. So again, if we compute this in coordinates, it looks like this. Maybe I can erase this example since it's not very useful. So it's this computation right now in coordinates. So in this vector notation, it can be written in a condensed form like this. And if our U satisfies the Laplace equation, then this vanishes. We are left with that only term. And here we can apply Stokes' theorem, writing it as an integral on the boundary. So if we do the same computation here, then again this vanishes because it satisfies the equation. And in this integral, we can compute it, for example, for the cube. So if it is an integral from 0 to L, all this. And for example, for the first integral, it will be ux of L y z integral in dy dz from 0 to L minus integral from 0 to L u x of 0 y z dy dz plus and so on. So these integrals correspond to integration over different faces of a cube. Well, I can't draw it properly, but there are those are two different faces. Maybe I can try. So one face is this. X, Y, Z. So it is this face. mm, for fixed x, uh, and for all y's and z's from 0 to L. And here the same phase located at 0. Oh, sorry. Yeah. We get something on the boundary, and the general formula looks like this. So if our U satisfies zero boundary conditions, then it equals to 0. Uh, Therefore, solution of this equation with zero at conside and zero boundary conditions is constant. Gradient of U equals to 0. U equals to constant. And it's the only possible non-uniqueness of solutions uh, uh, because in principle we could have only Neumann boundary conditions, only derivatives, or we could have periodic boundary conditions. So in that case, arbitrary constant would also be a solution of this equation. So sometimes the Laplace equation solution of the Laplace equation is defined up to arbitrary constant. So it is possible. And also one more remark that in such situations there are some restrictions on the right hand side of this equation to have uniqueness. In the sense that if we have Laplace of u equals to f, then we can integrate this integral over domain Laplace of u is integral over this domain f, and this left hand side can be written as the integral over boundary of this domain dn gradient u equals to integral over df. So if we have Neumann boundary conditions only, then this is something fixed, and this is something fixed. So they should be consistent. Or another option is that if you have a closed surface like torus, and there is simply no boundary, then the left-hand side should equal to 0. So the right-hand side should also be 0. So the only restriction. Uh, hmm? It is one possible option, yes. Hmm? No, this formula works always. But if you fix u at the boundary, then this it can be anything. It is not fixed. It will adjust somehow to the right hand side and to boundary values. The only problem appears when we fix gradient and not u itself. Hmm? No, in principle, this can be Rn with some periodic boundary conditions. So like, Uh, what do you mean by uniqueness?
The domains are random.
Ah,
What type of condition we can set?
In that case, we will study this later. So, namely, we can say, of course, that this function should decay fast enough at infinity, but it's not the only reasonable boundary condition. We can ask, for example, for functions to grow linearly in some direction, or to have some specific asymptotics. For example, logarithmic asymptotics in the two-dimensional case. So, um, and this uniqueness questions should be discussed individually, because uh, so in that case, we should impose such conditions that they kill the space of solutions of homogeneous equation. So, is it fine? So, now let's consider the simplest possible case, the heat equation. So probably I can erase this. So in this case, everything is even simpler. We can simply study the time derivative of the integral for u squared dx, dnx. So this well, 1/2 u squared will be integral of u Laplacian of u dnx. So now we want to integrate it by parts back. So we write that it is gradient of u gradient u minus gradient of u squared dnx. So the first part can be integrated by parts, and the second part stays as is. So this is dn u gradient of u minus integral gradient of u squared dnx. So this equals to 0 because of boundary conditions, which are even directly on Neumann. Doesn't matter. And this part is strictly less than 0. Or less or equal than 0. Equality is achieved when u is constant. So in this case, it is even better than for the wave equation. We have some functional that strictly decays, and if this functional was 0 at the beginning, then it stays 0 forever. So u at then if u at 0 and x was 0, then u of t and x is 0 as well for any time. Uh, so this was all about existence and uniqueness, but this functionals oh, actually this energy functional will be useful in the future for technical reasons. So the statement which we will learn the next time is that Laplace equation actually describes the minimum of this functional, and as we know this description, we can use this functional to change the coordinate system, because it is much easier to change coordinates in something which has only first derivatives than in the equation itself. So we can use this approach to pass to, for example, spherical coordinates. So, and there will be also one more statement about the energy function for the wave equation, that this this total energy is distributed between different modes. So it is kind of obvious because they oscillate independently, but it can be checked by explicit computation of the energy. Okay, so do you have any questions about this? Okay, thanks for your attention. See you in the next week.